Okay, next we have Jules Hedges talking about non-compositionality in categorical systems theory. Take it away, Jules.
Okay, thank you. Hello, I am the disembodied voice known as Jules. This talk is going to be about 50% mini tutorial in how to think about general systems theory using categories and monoidal categories. And in particular, a problem that quite often comes up where functor reality fails because of emergent effects. And then the second half will be a proposed workaround. It's not really a solution, it's a proposed way of brushing the problem under the carpet. And I'm not going to claim that the solution I'm going to present is a good solution. I'm going to claim it's a solution and throw it out to everybody to see what they think. Okay, so in applied category theory, we very often build categories where our morphisms are some variety of open systems. And in this talk, I'm going to be extremely generic about what I consider to be a system. A system is something that can behave. That's what a system is. So if our morphisms are open system, an open system is a system that can communicate in some way through a boundary with the outside world, which is the stuff that is not the system. And so our objects are going to represent the boundaries through which the system can communicate. So in categorical systems theory, we arrange that an open system has a left boundary and a right boundary. And that's often a little bit artificial. The question, why do we make these form a category rather than some other kind of object? And the answer is really that we don't need to. There are other possibilities given by other operad algebras, but categories turn out to be a very convenient way. The categories have lots of nice properties. So when we couple, so composition is going to be coupling two systems along a shared boundary. And this forms a complex system. So a complex system is a complex of systems. So a complex system doesn't mean a complicated system. It means a system that's been composed from smaller parts, a complex of systems. And often we also have a disjoint, a non-coupling composition, and that's going to give us a monoidal category as a general rule. So I'm not committing myself to any particular flavor of systems, so I can't say anything very concrete about what this category can do, but often you get monoidal structure, compact closed structure, hypergraph structure, this kind of stuff. And as a side remark, as well as systems theories and applied category theory, we often also have process theories where the left boundary is the inputs and the right boundary is the outputs. So the difference is that in a systems theory, I think of categorical composition in the category as being along a kind of spatial dimension, whereas in a process theory, it's along a time dimension. So first one thing runs, then the other thing runs. But most of what I'm going to say will apply equally well to process theories as to system theories. And I'm going to generically call them all systems theories. Okay, so I said that a system is something that can do a behavior. So given a boundary, we want to associate a set of possible behaviors that we can observe on that boundary. And I'm again going to be extremely generic about what this means. And that means that to an open system, we want to associate a relation between the behaviors on the two boundaries, where two behaviors, one on each boundary, being in the relation, I'm waving my hands and just realized that you can't see me because I don't have a webcam. Two behaviors being in the relation means that it is possible to simultaneously observe those two behaviors on the two boundaries. And we take the principle that you can't observe the system directly, you can only observe the behaviors on the boundaries. So this looks like it wants to be a functor into rel, but so what actually happens, so suppose we have two systems which we're coupling along a common boundary, and they can behave in ways that share a common behavior on the common boundary. So we have a behavior A and B of F and a behavior B and C of G for some behavior be on the middle boundary? Usually, if you're in a half decent situation, this is going to apply that the complex system FG, I'm writing composition forwards here, you can observe the behavior A on the left boundary and C on the right boundary. If your systems theory doesn't satisfy that, then you should probably give up and try something different. So this formula, AB and B of F and BC and B of G for some B, this is the definition of composition in the category rel. So what this means is that B of F compose B of G in rel is a subset of B of FG. So every behavior that can be formed by composition in rel is still a behavior of the composite system. I was going to switch these two slides and didn't get around to it. Unfortunately, the converse often fails in practical situations. If you have a complex system FG, this can often exhibit emergent behaviors which don't come from individual behaviors of the two parts that agree on the common boundary. So we can define an emergent behavior of a complex system, and formally that's with respect to a particular choice of composition FG, to be an element of, you probably can't see my mouse, but I'm circling this formula, an element of B of FG, which is not an element of the other thing.
By the way, Jules, we can see your mouse.
Oh, that's good. Okay, thank you. So we don't have a functor into rel, but in fancy terminology, we have a lax functor, where we're viewing our category of systems as a two category in a degenerate way, where we only have one two cell of each type, and rel is a locally post-settled two category. So lax functor is the fancy name for what this is. Unfortunately, in practice, lax functors are much less interesting than actual functors. And the true functoriality can fail quite badly sometimes. Sometimes it fails worse than others. So I have a grand challenge for applied category theory, and many of you will have heard this before, which is, given this situation, given a category of systems and a lax functor into rel, or something like linear relations or additive relations or something like this, a more quantitative version, instead of just saying, oh, it's a functor, or oh, it's not a functor, but it's a lax functor, can we get a finer grained description of things in between? Can we describe how badly functoriality fails, so how badly the laxator fails to be an isomorphism, in a useful way, where useful means it tells us something about emergent behavior which is interesting from a systems theory point of view. Okay, I'm not going to talk about this. This is a hard problem, probably. Okay, as an example, so there are heaps of examples of this. I'm going to talk about reachability in open graphs, because it's a problem that lots of people think about, and also it's very easy to draw pictures of, which is nice. So open graphs, there's a few equivalent ways of defining it, and there's also some different ways of defining it which are different. I'm going to take my objects to be finite sets, and my morphisms are going to be graphs together with a cospan of graph homomorphisms from the discrete graph on the boundary sets. So that means that we have a graph together with some identification of some nodes in it as the left boundary and some as the right boundary, potentially in an overlapping way. So this is the structured cospan way of defining open graphs. So we would like to talk about reachability, where behavior means something like you stick a token in somewhere on the left boundary and you allow it to move non-deterministically, and then you observe where it could potentially come out on the right boundary. So we take the behavior on the boundary to be the potential behaviors just to be elements of that set, saying where the token appears. And a morphism, given an open graph, we're going to say that two boundary vertices are related just when they're reachable from each other in the graph. Here by graph, I'm meaning non-directed simple graph, but this is just a generic representative of a whole class of reachability and graph-like structures. So this includes things like Petri nets. This thing is a lax functor into rel. It is not a functor. And the reason it's not a functor, so here is the obstruction to it being a functor. It's this zigzag where you cross a boundary 3 times, you go back and forth. So if you look at it, the only node reachable from here is this one, and the only node reachable from here is this one. That's the only node reachable from here in the left component is this one, and the only node reachable from here in the right component is this one. So if you do this compose the reachability relations, you get the empty set. There is no single vertex on the middle boundary where it's reachable from both of the 2 sides in the 2 individual components. But we have reachability in the composite. Okay. Okay, so now I'm going to talk about my proposed solution. So my proposed solution is that it doesn't make sense to ask what is the behavior of an open system just by itself in isolation. You need to talk about the context in which that system is behaving. So I'm going to use the word comorphism for a context into which a morphism can sit. So I'm going to write C upper bar. I'm going to put an upper bar over the hom set to mean the set of contexts into which we can put a morphism from X to Y. And in a string diagram, a morphism is a box. So it's an inside with a hole on the outside. A comorphism is that inside out. So it's everything apart from the box. So the idea is that when we put a morphism into the context, we insert one into the whole of the other. And later this week, you'll probably see some people drawing comb diagrams, and you can also draw these as comb diagrams alternatively, which is the same as this, but you cut the bottom off. Okay, so my C upper bar had better be a functor of this type, because say I have 3 morphisms and then we have a context for the composite of these 3, what I can do is I can view F and H as part of the context of G. So there's 2 different views. I can take C as the context of the composite FGH, or I can view the thing in red as the composite of G. As the context of G. So this is just saying that C upper bar is a functor from C cross C up to set. And because I'll need to write this a bunch and this is ugly, I'm going to introduce F lower star and F upper star as just notation for applying this C upper bar functor, which I'm going to call the cohom functor. Not to be confused with cohomology, cohomomorphism. Okay. Often if we have a monoidal category, then it's not enough that this has to be a monoidal profunctor or a Tambara module or something. We need operations of these 2 types, which says that if you have 2 parallel morphisms, you can, you can do this. You can view one of them as part of the context. And these need to satisfy some naturality conditions, which I haven't written down here. Okay, there are some general purpose examples of this sort of thing. So if C is a monoidal category, then one example of a C upper bar functor you could define is this thing. This thing is a co-end in the category of sets. And tomorrow morning there'll be a talk on optics. So this is a state in the category of optics. And what it looks like is this. A context consists of a state and a co-state, and they can also communicate through some kind of passing channel that bypasses the system. And this coend is just saying that you're allowed to slide things along this wire and it makes no difference. If you're not just monoidal, but you're also traced monoidal, then it is consistent to, you may define a comorphism to be just a morphism going the other way. You need a trace in order for the relevant conditions to be true. If you're a compact closed category, you can rearrange that just to be a joint state on the input and the output. These are general purpose things that you can do in any category. Okay, so suppose I have my category of systems and I have my, what I want to be my semantic category, which is usually going to be rel or something like it. And we're going to have a mapping on objects, which is to say boundaries. I'm going to define a thing which I'll call the augmented semantic category by, well, the objects are going to be the objects of C, and the morphisms are going to be pairs consisting of a morphism of C and, for every context into which I can put a morphism of C, a behavior. Then I can define identity morphisms. An identity morphism is the identity system together with the behavior that does the identity behavior in every context. And then composition is by this formula. So this is, what I do is I take the left system and I get its behavior in the context given by adjusting the context using the right-hand system. And then I take the right-hand behavior in the context given by adjusting with the left-hand behavior. And then I compose it in D. So this is where I regret drawing composition implicitly, but this here is composition in D. Okay, so this thing admits a forgetful functor to C, where we just take the system and forget the behavior. My proposal is that we view this C hat as our semantic category, and we would like our semantic functor into this to be a section of this forgetful functor, which is to say, to a system we associate a collection of behaviors in every context. So being a section just means that the first thing, the system part, is just the thing that you started with. So my dubious claim is that this is a workable framework for getting a functorial semantics in settings where nature doesn't want you to have a functorial semantics. So this doesn't solve your problem. It sort of it puts your problem in a box. It's sort of its way of controlling emergent effects. So you get functoriality by the back door. And by the way, this is about 50% of how open games work. Open games is lenses plus this. So Nash equilibrium is admits emergent effects, and open games work by a trick, which is basically this. So this all is reverse engineered from the category of open games. Okay, it's easy to prove that if you have a family of functions given, given every system and every context of the right type a behavior satisfying the obvious conditions, then this does indeed admit a functor, which is a section of the forgetful functor. So as an example, if we take reachability, and this part is a little bit sketchy. This is not necessarily a good example. So we could take one of the general purpose ones, for example, open graphs form a compact closed category, so we could take joint states. But as something ad hoc, let's take the set of the context for an open graph from X to Y to be precisely the set of open graphs with boundaries X and Y, but whose set of nodes is exactly the disjoint union of X and Y. So there are no additional nodes. And this is supposed to capture reachability. So we have our open graph in the middle, and then we have some stuff around the outside, which is the context into which we put it. But instead of remembering the entire graph in the context, we just remember reachability in that graph. So this this graph with no other nodes is representing the reachability of a bigger graph.
Hey, Jules, you're now cutting into question time.
Right. Okay. So given this, we do this, and I thought I might not have time for this, so I can stop here.
Great. And everyone can now unmute themselves, and thanks, Jules, for the talk. Questions, anyone?
Yep. Can I ask?
Go for it.
Okay, so I'm curious to understand, how do you think this framework can help with the fact that context is often a heuristic and not something really precise? Like, you give the example of reachability, but the example of reachability is somehow, I think, skewed, because reachability is still a very, very well formulated question mathematically. So in this sense, you already know what the emergent effects are and why everything goes wrong. So I guess that with this idea you can control it, but I think the main problem, that makes categorical composition insufficient in many contexts is that we haven't a full description of the problem. We are not even able to mathematically fully formalize the problem. Like, if
maybe we can let Jules try to answer, since we only have a few minutes.
Yeah, well, I don't have an, I think you're right, basically. I'm not claiming this as a silver bullet, but as a framework, I guess. So if you, yeah, I mean, this example, which I skipped over at the end, is just like that this is a very ad hoc thing, and I expect it to be worse. So what I've done is worked out the axioms that need to hold in order that you get a functor.
Yep.
But coming up with something that satisfies those examples is still a creative problem.
This is James Fairbanks. Hopefully I can ask a second question. For looking at this obstruction to the reachability in open graphs, it looks like what is well behaved is the set of paths. Like just the fact that you can reach here from there is less well behaved than the set of all paths by which you can reach here from there. Does that relate to this technique? That kind of set of paths should be better behaved than the reachability relation?
That's probably true. There is going to be another talk later this week on reachability and Petri nets, I think, possibly by Jade, but I'm not sure. So there is a better solution for the particular case of reachability and Petri nets in the literature, which possibly is what you're describing.
Oh, you think you could reverse engineer that technique, apply it to open graphs,
possibly,
and you recover this path, the set of paths thing, rather than just the reachability relation? That would be interesting.
That may be. And this I was using reachability just as an example that it's easy to draw pictures of.
Right.
And Jules, would you mind putting a reference to that in the chat after your talk?
Yes.
In fact, on that note, I think we should probably have you stop sharing and move on.